Hello, everyone. Welcome to the next session or the next lecture of the Machine Learning Teach by Doing project. Up till now, we have looked at several lectures for regression, and I thought it would be a good learning opportunity to make a separate lecture which describes the summary of the important things in regression and also gives a recap of whatever we have learned so far. This will be useful if you are preparing for interviews. Instead of going through all the lectures separately, you can go through this concise lecture to revise your concepts. So let us start. We will be looking at four things especially. We'll be looking at ordinary least square. We'll be looking at regularization. Then we'll be looking at gradient descent and stochastic gradient descent. And finally, we'll be looking at training versus generalization error. So let's start with the problem at hand in the first place. The linear regression problem looks something like this. We have XY pairs and we have to find that hypothesis which not only classifies the training data, not classifies, I should not use the word classifies, which not only has a good prediction on the training data, but it has a good prediction on the test data as well. So in the case of one dimensions, the hypothesis might look like this. So the general form of the hypothesis is y is equal to theta transpose x plus theta naught. And the main word which is used throughout regression is predict. So we are really interested in predicting new things. If we have been given the data of weather up till now, we have to predict the weather at a future time point. If we have been given the data of stock prices, let's say all of these points are stock price data, and if I give you a new x point here, which is the input, can you predict the stock price at that particular date? So the key word in the regression is prediction. So it is very different from classification in that sense. So this is our hypothesis class. Our loss function is the squared loss, which is basically the hypothesis minus the actual whole square and summation over all the points. And analytically, this loss is also represented as L of theta comma theta naught is equal to sigma I goes from 1 to n uh, theta transpose x xi plus theta naught minus yi the whole square. Basically, we find the hypothesis prediction and the true value. We subtract it and take a least square summation for all the points in our data set. That's the loss function. One more thing which is frequently asked in interviews is why do we use a squared loss function and why not a modulus loss function? So the key difference between these two is that the modulus loss function looks something like this, and the squared loss function looks something like this. The reason we don't use the modulus is that this is not differentiable at x equal to 0, not differentiable, and generally it does not have good properties. So that's why. So this is modulus of x and this is equal to x square. That's why x square is used and modulus of x is not generally used in regression for loss function definition, because the absolute function is not differentiable at x equal to 0. Very key point to remember. Okay. Now let's move to the objective function. So the case 1 is no regularization. The case 1 is no regularization, where the objective function j then just becomes our loss function, which is equal to sigma. Oh, I should add 1 by n here. 1 by n, I goes from 1 to n, theta transpose xi plus theta naught minus yi the whole square. The main idea here is that we want to find the theta and the theta naught, which is also called as theta naught, theta star and theta naught star. These are the optimal values which minimize j. Now it turns out that This particular problem of finding the minima of the squared loss in regression is also called as the ordinary least square. This is also called as the ordinary least square problem. And the beauty of this problem is that, so it's also called OLS. And the beauty of this problem is that it has a closed form analytical solution, which is not true for many machine learning algorithms. And this is how the closed form solution looks like. So first we have to define new matrices. So we define a W matrix like this. We first have a column of ones. This is, let's say, my first point x1. uh, this is my second point dot dot dot, this is my last point xn. I'm doing this for the case of one dimension. Then we define another vector called as t, which is the target values, and that just a collection of y1 to yn. The main thing here to remember is W has this augmented, it's called as the augmented matrix because it has this column of ones. The reason this one is there is so that theta can be defined like this: theta 0 dot 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 theta 1 and theta n. So this offset value is incorporated in a single vector, and that's why we have these columns of one here. If there are more dimensions, then it will just be added in the rows. So remember, the rows here is one training data point. So one row is one training data point, the second row is the second training data point, etc. But you have this column of ones. That's why always remember the dimensions. The first row is the first training data point, second row is the second training data point, etc. Once these vectors are defined, it turns out that once you find the gradient of this loss function with respect to theta and with respect to theta naught, and if you define j in terms of matrices instead of a vectorized summation, it turns out that the optimal theta star is given by this formula: W transpose W inverse W transpose T. This is the beauty of the OLS because it's a closed form solution. So we are lucky in this case. This luck won't keep on happening for other machine learning algorithms. Now it turns out that although we are lucky here to have a closed form solution, there are still problems with respect to the solution. And this is often asked in interviews. The first problem is that this matrix, if you look, it has the dimensions of d by d. So if we are in one dimensions or two dimensions, it's fine. The inverse is very easy to compute. But let's say if we do a feature transformation to a 15 dimension matrix, so the the time it takes to inverse a matrix is of the order of d cube. So if d is equal to 1, then the time is order of 1. But if d is equal to 10, so d is equal to 1, time is order of 1. But if d is equal to 10, then the time it takes to inverse this matrix is of the order of 1000. So it takes 1000 times more amount of time to calculate this inverse, and that's a big problem for us. Because the reason it's a big problem is because it will take a huge amount of computational time to calculate this inverse in the first place, and we don't want that. So that is the problem of the closed form OLS solution, and that is the reason why we move to the second thing which we are going to look at today. That is called as regularization. Well, another problem here is that what if the inverse does not exist? So it turns out that if the input features are correlated with each other, so for example, if one input is 1 comma 2, second is 2 comma 4, third is 3 comma 6, these are clearly correlated with each other, these inputs. So you can find one input based on another input, etc. So the thing is, if the input vectors are correlated with each other, then it turns out that it's very difficult to take the inverse. In fact, the inverse of that particular matrix does not exist. So what do we do in that particular case? So now we move towards regularization, and regularization actually solves two problems for us. The first problem which it solves is that it prevents overfitting. And remember, this can be asked in interviews. Why do we use regularization in regression? It solves two problems. The first problem it solves is overfitting, and the second problem it solves is the non-invertible problem. So, as I mentioned, if the features are related to each other, then the matrix cannot be inverted because its determinant is zero. So, regularization solves both these problems. The reason it solves both these problems is that, first of all, when we regularize, the loss function becomes different. The loss function j of theta theta naught is 1 by n, sigma I goes from 1 to n, theta transpose xi plus theta naught minus. So when I say loss function becomes different, I mean the objective function becomes different. It's the summation of the square loss plus this particular term, and this is called as the regularization term. This is that term which actually makes all of the difference. What this term does is that it penalizes having the magnitude of theta being too large. If the magnitude of theta is very large, it generally means that there are spikes in our hypothesis, and it means that our hypothesis might be overfitting the data. We don't generally want magnitude of theta to be very large. Remember this point. Regularization helps us to keep the theta magnitude small by attaching a penalty. And if the theta magnitude is small, our hypothesis won't go crazy trying to fit all the points. So it won't capture the noise, and that's why it will have a good generalization performance. The reason we do regularization is first to avoid overfitting, and to have, when overfitting is avoided, we also have good generalization performance. Keep this in mind. Now it turns out that in case of regularization, the optimized solution, which we saw in the no regularized case, it has a slight difference. So it looks like this: W transpose W plus N, which is the number of data points, lambda I inverse W transpose T. This is what is actually happening. The analytical solution for the regularization term actually looks like this. And the reason why it solves the non-invertible problem is that if you have a 2 by 2 matrix, let's say, which looks something like 2, 10, 15, and 15, and let's say this is my W transpose W. And for sake of simplicity, okay, so let me say this is also 2. So if you find the determinant of this matrix, it's not invertible because the determinant is 0. So this W transpose W is not invertible. Now, and you can see from the features are correlated. If you multiply the first feature by 7.5, you get the second feature. That's why it's not invertible. But now if you add this n lambda I, this will just become 2 plus n lambda, 2 plus n lambda, 2 and 15. Sorry, this 15 plus n lambda. Now, if you take the determinant of this, it's actually 30 plus 17 n lambda plus n square lambda square minus 30. So in the determinant, this term will survive. So the determinant is no longer 0, and it's possible for us to calculate the inverse of this matrix. Remember, that's the second thing which is solved by regularization. Regularization helps us to solve the problem if the features are correlated with each other, and regularization also helps us prevent overfitting. It leads to good generalization performance. One question which is commonly asked in interviews is that, let's say if you have this kind of a data set, so you have only one feature, but you use feature transformation to scale it to ninth order. So now you have x1 square dot x1 raised to 9 as features. The question which is asked in interviews is that what polynomial order do you need to use to fit these data points? Now, the biggest mistake in answering this question is if you say 9, then you will definitely fit these data points. That's very good. But this will lead to overfitting because this will fit all the points exactly. And it will lead to spikes in the data. This will lead to modulus of theta being very large. So we would not need such high power. Low power will not do because it will not capture the trend in the data. Ideally, we would like the power or the order to be not high and not too low, somewhere in the middle. So the correct answer is maybe x3 or x raised to 4. so that it captures the trend in the data, but it also is good at generalization. We will come towards this point at the towards the end of this lecture, where we see the difference between training versus generalization error, and this is the inherent struggle in all machine learning problems. So remember the benefits of regularization, and remember why regularization term, which has been added here, penalizes modulus of theta, and it penalizes from over capturing this particular thing. So let's say if this is the problem, and even if you use a ninth order term, but if you use a regularizer, then it won't go through all this data crazily like this. You can say in the interview that okay, I might use a ninth order polynomial, but I will impose a regularization term. That's fine, because then you will prevent the data or the hypothesis from being crazy, and it will still be good at generalization. So that's the second thing, regularization. The third thing is gradient descent and stochastic gradient descent. Gradient descent and stochastic gradient descent. So it turns out that let's say, even if you do this inverse, right, you still have to take the inverse of a d by d matrix, and that is still of the order of d cube, which is a big problem. If d is equal to 10, or if d is equal to 20, this is of the order of 1000, and that leads to very high computational time. So we do not want this. That's why we do gradient descent. In gradient descent, what is usually done is that uh, we start with a particular theta, and then we do this kind of a training loop. Theta new is equal to theta old minus some learning rate times gradient of j with respect to theta. Gradient of j with respect to theta old. This is the thing. Now, here if you see, if you find the gradient here of j, it turns out that you have to find the gradient for all of these data points. So it turns out that the gradient actually looks like this. Uh, it turns out that the gradient looks something like this. 2 by n sigma I goes from 1 to n theta transpose xi minus yi into xi. So it turns out that the gradient looks like this. Now the problem here is that uh, you have to do this summation for n times, and that leads to again higher computational cost. So remember, this is still better than d cube, because we do not have to take any inverse here. We just start with a theta, and we keep on moving in the direction of the steepest descent, and we hope that we reach the optimal theta, which gives the lowest value of this j. But people are not happy here also, because you have to do this n times. You have to take a summation over all the data points. So what if we have 1 million data points? So if we have 1 million data points, it means that we need to take this summation 1 million times, and that's a big computational cost. So people are not happy with gradient descent also. That's why we move to stochastic gradient descent. So what stochastic gradient descent says is that in this iteration, when you do theta old, theta new is equal to theta old minus uh, learning rate. So this is the learning rate, and you take the gradient at only one point. You take the gradient of f, or you take the gradient of j. Take gradient at only one point. You do not take the summation. Take gradient at only one point. Essentially what this says is that at every iteration, what gradient descent does is that at every iteration it essentially takes the average of all the direction given by all data points, and we move in that average direction. So let's say there are 10 points. Okay, if you calculate the direction of steepest descent for one point, it might be here. For the second point, it might be here. What gradient descent does is that you take an average of all these directions and you move in that direction. What stochastic gradient descent says is that no need to even take that average. For every iteration, you randomly sample, sample one point randomly, and you take a small step. You take a small step in the direction given only by that point. So no need to take average, no need to take the summation over all the points. You just move in the direction of that small, you take a small step in the direction given by one point. And although this means that we are not kind of moving in the exact correct direction of the steepest descent given by all the points, it's fine. We make some mistakes, but that will at least prevent the summation operation over 1 million data points. And it turns out that even if we take erroneous steps, which are not really correct, but if we take small steps in the direction given by one point, we actually reach, we converge to the minimum. And sometimes this really reduces the computational time. So I have done examples in which if you have 1 million data point, stochastic gradient descent is like around 700 or 1000 times faster than gradient descent, and both reach the exact same answer. One thing to note, which is also asked in the interviews, is that this neta of t, which is the learning rate, in the case of stochastic gradient descent, it's not constant and it needs to decrease with time. So we don't take a fixed step here. We take steps which go on decreasing with respect to time. So we take smaller and smaller steps as the number of iterations increase. So that is the main thing to note here in stochastic gradient descent. The step size is not constant, and only if the steps look like this, then theoretically it's guaranteed to converge. And if you look here, the time which it takes to do each iterations is very less, because you just have to find the gradient at one point. You don't have to do summation or n points. Of course we might need more iterations, but if you have 1 million points for linear regression, stochastic gradient descent is sometimes much faster than gradient descent. This is the third thing to note. So the main point in the third thing is that analytical solutions taking inverse is very hard. If the dimension is large, the time complexity of taking an inverse goes as d cube. So that's why it's not possible to take the inverse all the time. So we go with the gradient descent solution. People are not even happy with gradient descent. So that's why the final thing which we converged upon is stochastic gradient descent, which leads to good results and in a good amount of time, which is very less. Now let me come to the last point, which is training versus generalization error. And this is kind of a common tension in all machine learning problems. So let me try to explain this a bit better. This is called as training versus generalization. Now let me explain this problem to you, because I have seen it being asked in many interviews and candidates really getting confused. So let's say that this is my underlying data, and these are points who are given by x and y. So x is my input and y is my output. I tell you to find a linear regression model which best approximates the input from the output. And you decide that first of all you should be able to see that linear regression won't work here, because it clearly is a cyclic variation in the data. So you need a feature transformation. So you say that instead of x, I use x square x raised to 10 as my features. And then the question is, what is the best feature power which you should use? And this gives the so rather than training versus generalization, okay, let me try to explain it. Now if you have a higher power, if you have x raised to 10, it will of course fit this data exactly well, but it will lead to low generalization error, as we saw, because this might be overfitting. The magnitude of this theta will be very high, and it might be capturing the noise. So higher power of x would lead to lower generalization. But if you use lower power of x, if you use x raised to 1, then it might not even capture the structure of the data. So sometimes this is also called as the tension between structural error and estimation error. If you use a lower power of x, then it will lead to low structural error. Sorry, it will lead to high structural error, because we will not capture the structure of the data pretty well. It will be just like a straight line. We won't capture the oscillations, but it will lead to low estimation error, because the magnitude of theta won't be high and it won't have too many spikes. But if we use x raised to 10, this will lead to low structural error, because we will capture the structure of the data pretty well, but it will lead to very high estimation error, because this hypothesis will likely have spikes, and it will likely capture the noise in the data, and it won't do good on new data. So generalization or estimation means performance on the new data which this algorithm or hypothesis has not seen before. So this is the tension of machine learning. You cannot have order which is too high, because it will lead to high estimation error or high generalization error or new data points. You cannot even have order which is too low, because it will lead to high structural error and low estimation error on new data points. That's why you kind of need an order in the middle, maybe x to the power 3 or x to the power 4. So always keep this in mind, the tension between structural error and estimation error in regression problems. So whenever you prepare for regression, try to keep these four things in mind: ordinary least square, regularization, descent, and structural versus estimation error. Also, in some interviews, they ask you to code the regression from scratch, the ordinary least square. And we have done it in one of the previous lectures. So please go through that to understand it in detail. Okay, so I deliberately made this lecture so that instead of, if you're preparing for interviews, you can just go through this one video, uh, and it will be a good recap for you 30 minutes before the interview. So thank you so much. I hope this video added value to your life. I deliberately made it a bit fast because I wanted to keep it short, since it's for revision material. If you want to go through every single section in detail, we have videos for all of these in the previous lectures. Thank you so much, and I look forward to seeing you in the next lecture of the ML Teach by Doing. Thank you.